Okay, so thank you for joining us this month, CSSSA webinar. It is great pleasure to have Ketika Garg speak at our webinar this month. She's a multidisciplinary cognitive scientist with a background in biological sciences, and she has a broad interest in adaptive behavior, and her research focuses on how adaptive behavior unfolds at various scales of organizations, from individuals to groups. Her work uses foraging models where individuals or groups search for resources like food or information in the face of various constraints and affordances posed by their physical and social environments and cognitive capacities. She is currently a postdoc researcher at Caltech, where she extends traditional foraging paradigms to the emerging new landscapes of social media, which is really exciting research. And she's from India, but has lived in the US for the past few years, where she is still searching for the perfect samosas, which is kind of foraging problem. And I'm curious whether what kind of balance you have between exploration, exploitation when you search for perfect samosas. But Ketika, please take the floor.
Thank you, Jim. It is a real problem searching for the perfect. I've not been able to find a good one to exploit it enough, but I will live. And thank you for giving me the opportunity to talk about my work. So today, as Jim said, I will talk about some of the foraging models that I built during my time as a PhD student. And this work was in collaboration with my advisors, Chris Kello and Paul Smolino. Today, I will discuss the two closely related models of the same problem of collective search or foraging, but the two models also look at this problem from different perspectives. The search is a general feature of adaptive systems, whether it is for resources or food or information in problem spaces. Adaptive systems, organisms, they have to find things to help their survival or to make themselves better. And what makes search an interesting problem is that it needs to unfold within the constraints and affordances of the system. For example, the search costs like movement, energy, time, or opportunity costs. Without any cost or constraint, search is not really a problem, because the optimal strategy is to search every infinitesimal point in a space for an infinite amount of time with an infinite amount of energy. But that is hardly the case in the real world, where there are costs that the organisms need to abide by, which makes the problem interesting. And organisms are often faced with trade-offs between advantageous but conflicting options, such as the ubiquitous trade-off between exploring new possibilities and exploiting the already known options. But in groups, individuals can learn from each other. They can share resources, they can share information, which can cut down their search costs and make them more efficient. For example, in collective foraging, such as in social insects like ants and bees, individual organisms can find resources, but they can also share the information. And especially if you're not successful, they can socially learn about the location of resources from other group members. Another example of this phenomenon can be collective problem solving. Say, a team of individuals is brainstorming for a solution to a problem, while each individual agent or individual team member in this team can do trial and error searching to find solutions. When they share information and converge upon a solution, they can also assess it better than an individual would be able to. But collective searching or foraging or problem solving comes at its own costs. It can be maladaptive if, for example, it prevents the discovery of new and better solutions, which cause the group members or team members to converge onto suboptimal solutions. And these costs and benefits of social learning within a group can create new trade-offs. For example, now a social searcher has to decide between following social information or social learning and between independently searching. And it can also modify the existing trade-off, like the exploration and exploitation trade-off, which always exists in a search problem. And this interplay between the two trade-offs and the optimal balance can also depend upon the problem space or a given task. For example, if solutions are easy to find, then there's not really any point of social learning, or there's not much point of exploring the landscape or problem space at great personal cost. So then the question is, when is it beneficial to collectively search? And how can individuals in a group collectively search in an optimal way that manages these trade-offs? And to study this, we built a spatial model of collective foraging, where agents have to search for resources, and they can do so by independently searching based on their intrinsic search strategies or by socially learning from others. And we designed the model so that it can accommodate different physical and social landscapes. So we manipulated the resource distribution, group size, and then we studied the search behavior as spatial movement in that landscape. So zooming into the model, imagine you're a forager searching for these fruits, these berries in the bushes. And because you're in a group, you can also see the other forager, your fellow team member, who has found these berry bushes. And as an individual agent, you have foremost two options to find food. You can either socially learn, follow the other team member, or you can independently search. If you choose to do social learning, it can reduce risk and search costs that come with independent searching. It can make the harvesting of the resources better, or better assessment of the solutions, because now there will be collective effort concentrated into one space. But it can also decrease collective discovery of new and possibly better resources or solutions. And in the worst case scenario, it can lead to everyone converging onto the same solution and cause informational cascades, which can be maladaptive. On the other hand, independent searching via trial and error kind of search strategy can pose a greater risk, but it can also increase chances of discovering new resources and prevent cascades. But when independently searching, there's another choice, whether to exploit nearby, near to where you are, which will decrease your risk because you're not venturing out in the open world. You can improve solutions, you can focus your efforts in a limited space, but you can also get stuck in local optima or poor patches. Or you can choose to explore distant areas at greater risk, but the possibility of encountering novel or better solutions increases, which is also helpful for the group because it can promote collective discovery. So to model the first trade-off between independent search and social learning, we used a parameter alpha, which when plugged into this equation, determines how much social learning agents practice in the model. And by high social learning, when the agents practice high social learning, that means in this particular model that agents don't care about the cost, which is related to the distance of another agent. So irrespective of how costly it is to walk to where someone else has found food, the agent will always pursue it. In low social learning, they are very rarely motivated to follow another agent, irrespective of its benefit. And in selective social learning, they only follow a cue when it is close enough. So in a way, the selective social learning in this model is a mechanism to filter out costly information. To model the second trade-off at the level of individual search, we use the Levy-Walk model, which is a general random search model, but that it generates different search strategies as a continuum from explorative search to exploitative search. So for example, here in black, can you see my cursor? Yeah, okay. In black, you can see the explorative strategies, which are like straight path lengths with few turns, and they cover a lot of ground in a limited amount of time. On the other hand, we have in the red, the exploitative movements, which in the same time have only focused their movements in that small space because they keep on looping and searching around where they are. So getting into how these trade-offs play out in the model, what exactly happens in the model. So whenever an agent is not on a food batch or a resource batch, it asks whether someone else is on food batch. And if there is someone else on the food batch, it calculates the probability of social learning or following that social cue. And in the condition of high social learning, the agent will almost always follow the social cue, irrespective of the distance d. In the condition of low social learning, it will almost never do that. And in the case of selective social learning, it will depend upon how far the other agent is. Then it will roll the dice, and if the probability of social learning is greater than random chance, it will begin its journey step by step. And if while walking over to another agent, it discovers another closer agent who already found a resource, it will switch to follow it. But if it chooses to independently search, if it does not decide to follow anyone else, it will draw a step length from its random walk distribution. And based on the given strategy, it will be short step length or long step length. And then it will start moving in discrete steps of fixed length until it completes moving the length L. And again, a long L will take it far in a straight line, while a short L will restrict it closer to its current position. And at each step, if it finds a resource, it will truncate its movement. And if it finds another successful agent at a resource batch, it will again calculate the probability, roll the metaphorical dice, and decide whether to engage in social learning or continue its solo journey. Getting into the results. First, we looked at the effect of problem space or the resource environment. Here we can consider two kinds of problem spaces. One where the solutions or the resources are correlated or clustered, for example, here. And in another case where they're not correlated and they're kind of uniformly distributed. So we found that when the resources or the solutions are uniformly distributed, there's not really any advantage of social learning. And it's better to be more independent, which are the two rightmost points here. And this is because when it's not clustered or correlated, the probability of finding a solution where you've already found one, the probability is really low. So there's no benefit of really following someone else. But when there is correlation in the problem space, then it is beneficial to engage in social learning because you will increase your chances of finding a solution close to where others have found the solution. Next, we looked at the effect of the search strategy, the second trade-off between exploration and exploitation. And as it has been shown in many previous works, we found that when there's no social learning, it is beneficial to engage in a search strategy that balances explorative and exploitative search strategy so that you go far, but you don't go too far. And the chances of you looping back remain, which is in the green line here. But in social learning agents, when they follow each other, then we found that it is substantially beneficial to engage in explorative search. That is, for an agent, it's beneficial to follow someone, to exploit the social information, but then also independently explore other parts of the landscape pretty quickly. And to understand how this works, we can look at what happens in the model. So say an agent is at a batch of resources. It is eating one berry bush at a time, and it signals to other agents that, hey, I have found this solution, this resource, and other agents join. And as other agents join, the current agents in the patch, they stay there for longer duration because they are finding more and more solutions. And as this cycle continues, more and more agents join and they stay longer, they emit social information, which is great to find, to extract resources from this solution or this patch, but it diminishes the collective discovery and exploration for other patches because it aggregates and localizes the agents to one area. And this effect gets exaggerated based on the independent search strategy. So when agents practice exploitative independent search, where they do not move too far, they just stay close to where they are, then we can see, so in the green are the resource patches and the triangles are the agents. So an agent found a resource here and everyone coalesced, converged, and they exploit that resource patch. But then after the exploitation of it, they're not able to disperse away. They remain stuck in that local minima. And all these resource patches remain to be explored. But when agents practice explorative search, then they take advantage of converging and extracting resources from one patch, but then after they exhaust that patch, they quickly spread out, disperse away, break away, and resume independent exploration for other patches. But based on the social environment or the task space, it is possible that in certain scenarios, the social information is too high, which decreases the overall independent search, even for the explorative agents. And to test this, we increased the group size from 10 agents to 50 agents, which amplified the social information present because there were now more opportunities to join others because there were more social cues and the likelihood of finding solutions. So in bigger group sizes, you could really see the informational cascades because now everyone will just converge onto one solution. So in this case, we found that agents needed to be more selective. It was not enough to be just explorative. It was beneficial to not follow every social cue and filter out the costly information, to not move great lengths, but restrict yourself to a certain part. So we can see again why this happens. So when there's high social learning and the group size is 50, all the agents kind of coalesce together, which leads to high collective over-exploitation of the resource patches. And even after they they harvest some of the resources, they again quickly converge. And these are 50 agents converging onto one resource patch. But when there is selective social learning, they do not converge into one big group, but they maintain like small subgroups. They divide their efforts into different parts of the environment, kind of like a parallel computing task. They're like parallelly exploring and exploiting the different solutions, which greatly increases their efficiency. To summarize so far, we found that to maximize group efficiency, agents need to increase their explorative independent search when they're socially learning. And by increasing their independent exploration, they can prevent overlapping with others and increase their informational diversity. And they can also escape being stuck in a local minima. Further, we found that when independent search decreased in large groups due to the now amplified social information, agents needed to decrease their level of social learning to be more selective about which cues to pursue and prevent informational cascades within the group. So far, all the agents in a group searched using the same strategy, and the strategy they adopted affected the group performance. However, these strategies that maximize group efficiency, they may not be as beneficial for individuals within the group, especially if multiple individuals are competing for the limited resources. And in that case, the social environment, which is composed of the other agent strategies, becomes more important because now it will depend, an agent's fitness or search efficiency will depend upon what other agents are doing. So to test how individual search behavior is affected by being in a group, we created an evolutionary model or extension of the existing model, where all agents practice the same level of social learning, but their search strategy in terms of exploring or exploiting could be different, and it evolved over time or over generations. And their individual search efficiency defined their fitness. So they were not, the focus is not on the group performance, the focus is on the individual performance within a group, and to see how, which strategies for an individual is beneficial for its own benefit. We expected that exploratory search strategies, which were shown to be optimal in the previous model, then those strategies would be selected because it will be beneficial for the individual, they will find more resources, and it will be beneficial for the group. But we did not find that. We found that when there's social learning present in the right graph, the proportion of agents in the evolved groups is distributed over being explorative and exploitative, and more so towards being exploitative. So in other words, most of the agents, when they're fighting for themselves, when the selection pressure is on the individual, then the individuals are better off exploiting than exploring. And to understand why, we need to consider how the strategies evolve in the model. So we found that the evolution of search strategy between exploratory and exploitative, they kind of follow a cyclical frequency-dependent dynamic, which means that the payoffs or the advantages of a given strategy depends upon how many agents are practicing it within that group at that particular time. So, for example, if there are a lot of explorers present in the group, they are efficient at discovering resources. That is beneficial to them, but it is also beneficial to the non-explorers, the exploiters, who can now gain advantage and harvest the resources discovered by the explorers. And when that happens, the proportion of exploiters increases and the explorers decrease. And when the explorers decrease, the payoff from exploitation decreases, because now there are not any resources left to harvest, because exploiters cannot really find the new resources. They can only find very few. So it continues in like a cyclical, fluctuating dynamic. And whenever the group is composed more of exploitative agents, for example, in this graph between 500 to 1,000 generation, that coincides with the low group search efficiency in the green here. So overall, the group performance also goes down when there are exploitative agents present. But when there are explorers present, even for a limited amount of time, the search efficiency sees a bit of a jump. And in fact, due to the higher proportion of the exploiters in the evolved model, when compared with the previous model, which is the optimal in this graph, you can see that there's a substantial decrease. So when that same model was put under an evolutionary algorithm, and the selection pressure was at the level of the individual, the groups were not able to optimize the collective search. And that's because reliance on social learning promoted the selection for exploitative search strategy rather than the explorative search strategy, which is actually what drives the benefits of collective search in this model. So we hypothesize that whether group efficiency will increase if somehow, through some strategy, explorers can adapt their trade-off between exploring and exploiting to increase their individual payoffs and prevent the exploiters from taking over. And to do that, we created a new adaptive strategy where explorers were able to find the resource, but then once they found it, they were adaptively able to switch and briefly exploit the solutions of the resources they found before exiting that patch and exploring other resources. So in a sense, before other agents can join, the agent who has put in the cost to find a resource patch should be able to extract some of its rewards, to reap its rewards. And then we tested how this adaptive trade-off affects the group efficiency. And we found that indeed, when in the evolutionary model with adaptive trade-off between exploration and exploitation, the group efficiency increases because now the explorers are not driven out by the exploiters. Explorers maintain an equilibrium, evolutionary stable strategy so that they remain consistently in the population, and they do not, and they continue finding resources for the group and for themselves. So it's like a win-win for both individuals and the groups. To summarize, and going back to our initial question, searching for information or resources together as a group can be beneficial to individuals, especially when the resource space or the problem space is correlated. And when the independent search strategy is explorative so that it does not overlap with others, it maintains informational diversity and does not get stuck in local minima. And when there's high social information present, it is also beneficial when social learning is selective, that it filters out costly information. But collective search can also be detrimental when there's too much social information available and social learning is not selective, and when it leads to the selection of exploitative strategies, as we saw in the evolutionary model. That is when there's discrepancy between what is beneficial for the group and what is beneficial for the individual. And the other question of how can individuals collectively search in an optimal way by balancing these trade-offs. We saw in the first model that to achieve beneficial collective search, these two trade-offs should be managed, and the level of exploration agents engage in affects how much social learning is optimal, and vice versa. But when there's selection pressure on the individual level, for example, due to competition, as shown in the evolutionary model, then the strategies beneficial for the collective search may not always be beneficial for the individual. In which case, the effect of the social environment becomes more salient, and the individual search strategy needs to be not only explorative, but it should also balance that with adaptive and brief exploitation of the resources discovered. Thus, the evolutionary model also highlights that in collective search, there may be an additional selection pressure for strategies that are evolutionarily stable, which prevent free riding and maintain high group performance and individual performance. So to summarize in a very broad way, collective search for information or resources is a very general property of adaptive collective systems. And the path to efficient search is riddled with multiple trade-offs that groups of individuals must dynamically manage at both the individual level and the collective level, and also adaptively modulate them based on the problem structure and their social context. Thank you.